Hello everyone, welcome back to lecture series on aerospace propulsion. So in the previous lecture we were discussing about the supersonic intake, how do they differ from the subsonic intake, and what are all the design complexity we face when we start designing a supersonic intake. And then we have seen the different types of supersonic intakes, that is internal compression, external compression, and mixed compression intake. So we have classified these intakes based on where exactly we have these shocks present. If it is present outside of your intake, that is the external compression intake. If it is completely present inside your intake, that's what we call it as the internal compression intake. If you are having the shock at both inside as well as outside of your intake, means that's what we call it as the mixed compression intake. So after that, we have discussed about the operational modes of your supersonic intake. That is, instead of flying your aircraft in the design Mach number, if we fly in the Mach number less than the design Mach number and Mach number greater than design Mach number, how does or what is happening in that supersonic intake? We have seen that's what we call it as the operational modes of an supersonic intake, and that we have seen subcritical, critical, as well as supercritical mode of an supersonic intake. Okay, so when we are discussing about that supersonic intake, we have seen, irrespective of that intakes, you need to have a series of shock waves, that is series of oblique shock wave followed by an normal shock wave if you want to decelerate your flow from supersonic to subsonic Mach number, which required by your compressor. Okay, so in today's class, what we are going to see is that we are going to discuss about the starting of an supersonic intake. So what is the meaning of this starting of an supersonic intake? Is that basically it is to locate or place your normal shock wave at the required location. See, we have seen, right, in when we are discussing about the internal compression, external compression, as well as mixed compression intake, your normal shock wave should present, okay, at the Mach number where it is slightly greater than 1, so that you can have the least amount of total pressure loss when the supersonic flow is converted into subsonic flow. Okay, so what is this starting off supersonic intake here in sense? How do I situate that shock in the required location? It's not like you start your aircraft, automatically your shock wave will go on to present in the location where you need. You need to go through a certain process, then only you can establish a shock wave at your required location. So the process of situating this shock wave when your aircraft starts flying in the subsonic, and it becomes sonic, and then it becomes supersonic. How do we slowly move this shock wave to the required location? That is what we are going to see in this starting of supersonic intake. Okay, so let us consider an convergent divergent intake. Okay, so as you can see here, this is a convergent section. At the throat location, your area is minimum, and then it becomes divergent section. Okay, so let's say a case where your aircraft is just like a start flight, that is, it is climbing, or we will just say it is flying at a low subsonic speed. Right? If even if your aircraft is designed for Mach number 2, in order to achieve that Mach number 2, first of all, it has to go through this phase of subsonic flight and then sonic flight and supersonic, and supersonic it has to go to the design Mach number. Right? So let's say at the initial stage where my speed is very less. Okay, speed is very less means what is going to happen? Your Mach number is less. That is, my Mach number is less than 1, and that too it is very very less. You could say it is a low subsonic speed operation. Okay, so in the low subsonic speed operation, what is going to happen is that when the aircraft is moving, the capture area, okay, is going to be, what is your AA is basically it is the capture area. Okay, AI is the inlet area of your intake. Capture area is going to be less than your intake area. So because of that, what is going to happen? See, subsonic flow entering a divergent phase, your flow will be decelerated. Okay, but once it enters your intake, what is happening to your area? Your area is decreasing. In a subsonic flow, if the area is decreasing, means your velocity will be increased. Basically, your Mach number will be increased. Up to what location? Up to the minimum area location, your Mach number will be increasing. Okay. So after it increases, once again, what is happening? You are having the divergence section. A subsonic flow entering a divergence section, your area is basically increasing here. So your velocity will decrease. So obviously, your Mach number will be decreased. So as such, when your aircraft is flying in the subsonic, that is low subsonic speed, throughout your intake, your Mach number is subsonic. So obviously, you need the subsonic flow for your compressor, so you won't have any problem with that. Now, let's say I've increased my flight speed. Let's say become high subsonic speed become low subsonic speed become high subsonic speed. Okay, so when this Mach number is increased, what is going to happen? The difference between capture area and your inlet area will be reduced. Okay, but still, when your intake is entering your when your flow is entering your intake, your Mach number is still subsonic, but it's close to your sonic. So what is going to happen is that when the flow is subsonic, when they enter the convergence section, your flow will be accelerated. Okay, since already inlet Mach number itself very high, by the time it reaches your throat location, your Mach number m will be equal to 1. Okay, so m is equal to 1. So conventionally in your nozzle, as you know, a choking condition, once your Mach number reaches a sonic value in the throat location, what is going to happen is that you will have the acceleration after that, right? So that is if the divergent, the supersonic flow entering a divergence section, what will happen? Your flow will be accelerated. But here I kept my exit Mach number at my throat, your intake is less than 1. The reason is because there are two conditions has to be satisfied if a passage, a diverging passage, if it is going to accelerate your supersonic flow. Okay, that is one is your throat location, it should reach 1, and the pressure at the exit should be less than pressure at the throat. Your exit pressure should be less than your throat pressure. Then only your flow will be accelerating. If your exit pressure is more than your throat pressure, what is going to happen? Your flow will start decelerate. The reason why we are having deceleration is here because of the high back pressure. What is going to happen is that this sonic flow will start decelerate instead of accelerating. So that means by the time it reaches your exit, your Mach number will be reduced from Mach number 1 to Mach number in the range of 0.4 to 0.7. Okay, there is the Mach number you record for your compressor, right? So for this high subsonic Mach number also, what is going to happen? You have subsonic flow. 1 second it becomes sonic, but 1 second it becomes subsonic. Okay, now let's say my flight Mach number is equal to 1. That is sonic, right? So when it is going to be sonic, what is going to happen? You have an intake. Okay, so for this intake, as you can see here, you are it's kind of like a bluff body. Your intake size is very big. So when the flow supersonic flow is experiencing this obstacle, what is going to happen? There is going to be a shock wave will present, and that shock wave is going to be a detached shock wave. Basically, it is going to be a weak normal shock wave. Why do I say it is a weak normal shock wave? Is because here the Mach number is slightly greater than 1. So because of that, the wave which is going to form is going to be like weaker in nature. But even this we don't want, because it's not like you are going to fly your aircraft in the sonic speed, right? Even during this sonic speed, what is happening? Because of the shock wave forming ahead of your intake, okay, there is going to be a spillage. The spillage will result in what? It will increase the drag, that is spillage drag will be created. So as you know, when the supersonic flow is crossing the normal shock wave, it will become subsonic, right? So once it becomes subsonic, when it is passing through the convergence section, what is going to happen? Since your strength of your shock wave is very weak, the reduction from Mach 1 to subsonic will be released, and let's say it will be around at zero point 0.9 Mach number. So 0.9 Mach number flow enters inside a convergence section. By the time it reaches the throat location, what is going to happen? It is going to reach m is equal to 1. But due to the high back pressure, or due to the exit pressure of your diffuser is or intake is more than the throat pressure, once again your flow will start decelerate. So by the time it reaches the exit, it will be in the range of 0.4 to zero point 0.7. That's what we need for our compressor. Okay, now let's say my Mach number of my aircraft is increased. Okay, Mach number is greater than 1. Okay, so as you know, the strength of your shock wave forming in your flow field function of two parameters. One is your that wedge angle. Another one is the Mach number. Higher the Mach number, stronger the strength of your shock. So when I increase my Mach number more than 1, so the shock wave which is having a strong strength will be forming in front of your intake. So because of this, what is going to happen? Not only this spillage, this is going to create this spillage. Okay, because of this strong shock wave, when the flow is crossing this shock wave, what is going to happen? The total pressure loss also will be very high. Okay, but after crossing that also, what is going to happen? Your your Mach number becomes subsonic. So by the time it reaches your throat location, it will reach 1. Once again, it will start decelerate because of the your exit pressure of your intake is more than your throat pressure. So because of that, your flow will be decelerated. Once again, this also we don't want, because this condition creates two problems. One is a strong shock wave is forming in front of your intake, which creates the spillage as well as it creates the total pressure loss. Okay, now let's say I am having a Mach number, a supersonic Mach number. Okay, for that corresponding Mach number, what is happening is that this shock wave is pushed towards the intake, and this normal shock wave is forming exactly at the lip of your intake. Okay, so since it is forming exactly at the lip of your intake, what is going to happen? There won't be any spillage. But the problem is that the shock wave which is forming there is very, very strong. So you will have huge amount of total pressure loss, so which will reduce your pressure recovery factor P02 by P01. Okay, this also we don't want. So after that, so once your flow crosses your normal shock wave, it becomes subsonic. So once again, it will be accelerated through the convergence section. Will reach m is equal to 1 at the throat location. But once again, it will start decelerate because of the high back pressure. Okay. So what was our objective? Here itself you can think, so why can't we just use this shock itself? Why do we have to push our shock inside? It's because here the shock wave is forming at the location where your Mach number is very, very high. So that is going to create huge amount of total pressure loss. This location also we don't want. Okay, so now let's say I'm going to increase my Mach number far greater than this m. What is going to happen? Because of the high momentum of your flow, this shock wave will be pushed inside the intake, and it is going to form in the divergence section. Downstream, somewhere in the downstream location, it is going to form at this location. But here also we don't want. Here you don't have any problem. You don't have any spillage. M is greater than 1. Okay. But when it reaching the throat location, it will become kind of 1, because here a supersonic flow entering the convergence section, it will be decelerated. Okay. But after that, what is going to happen? When the flow is crossing, it will become subsonic. But the problem here is that once again your shock wave is forming at the location where your Mach number is very high. Now slowly I'm going to reduce this Mach number. Okay, I'm going to equate to design Mach number. So for that design Mach number, what is going to happen? The normal shock wave will form slightly downstream of your throat location. In your throat location, your m is equal to 1. So I'm going to locate or situate my normal shock wave slightly downstream, means there your Mach number will be say 1.01. So when this 1.01 flow is there in the normal shock wave is located over there, your strength of your shock wave is going to be very, very less. So when the flow is crossing, you will have least amount of total pressure loss. Okay, so you don't have any spillage. You don't have much of loss when the flow is converted from supersonic to subsonic. Okay, this process of how do we establish this standing normal shock wave slightly downstream of your throat location, what we call it as the starting of your supersonic intake. Okay, so it has to go through this multiple process if at all you want to situate your shock wave slightly downstream of your throat location. Okay, so in subsonic applications, you don't have any shock, so we don't have any problem, which is acting similar to that of the conventional subsonic intake. But once your flow becomes supersonic, you will have the formation of the shock wave. How do I move the shock wave inside my inside my intake, and place my shock wave exactly at the location slightly downstream of your throat? This process, what we call it as the starting of your supersonic intake. Okay, so next we are going to see about the performance parameters of an intake. So it's common for your both subsonic intake as well as supersonic intake. Okay, so what is this performance parameter in sense? Basically, what is the parameter we use to measure the performance of your intake? Okay, so whether it is a subsonic intake or supersonic intake, how do we measure? That's what we denote, or that's what we call it as the performance parameter. So what are the performance parameter, or what are the parameters we use to measure the performance of our intake? Or there are two parameters mainly we use. One is isentropic efficiency, another one is the pressure recovery factor. Okay, so what is this isentropic efficiency? Sometimes we call it as the adiabatic efficiency. Okay, so why do we call it as the isentropic efficiency or adiabatic efficiencies? Because we are finding out this efficiency which corresponds to the ideal process or isentropic process. Okay, so what is this isentropic efficiency? Basically, it is the ratio of ideal enthalpy change to the actual enthalpy change during the diffusion process. So across your intake, whether it is the subsonic intake or supersonic intake, we have the diffusion process. What is the meaning of diffusion process? Your flow velocity is being decelerated or reduced, when it is passing through the diffuser. So that process, what we call it as the diffusion process. So what is this isentropic efficiency? Is then that when you are going to decelerate your incoming flow, you have a intake. Let's say I have a divergent intake. So when the flow is passing through this, what is going to happen? You will have the boundary layer formation. Or to be precise, there is going to be a friction. That friction will result in the formation of boundary layer. Okay, so what is happening here is that when the flow is passing through that, there is going to be a increase in the enthalpy of your flow. Or there is going to be a change in the enthalpy. So what is this isentropic efficiency here is that it is the ratio between what is the enthalpy change during your ideal process, that is isentropic process, in sense there are no frictional loss or there is no loss in that particular flow process. So what is this H02? That is the total enthalpy. HA is the static enthalpy of your flow. The difference, what we call it as the change in enthalpy. So this change in enthalpy during the ideal process or isentropic process divided by change in enthalpy during your actual process. Actual process in sense, basically, since there is a solid body present in your flow, there is going to be a friction. If there is a friction, there is going to be a loss. The process won't be an isentropic process, right? So the ratio of this ideal process enthalpy change during your ideal process divided by enthalpy change during your actual process, what we call it as the isentropic efficiency. So if the enthalpy change during your ideal process is going to be less than enthalpy change during your actual process. So the isentropic efficiency is going to be always less than 1. Okay. So same other name you can call for this isentropic efficiency. You can call it as the adiabatic. If the process is not isentropic, you could say there is a process with loss, means basically that is the adiabatic process, right? So here you can say either it is an isentropic process or adiabatic process. Sorry, isentropic efficiency or adiabatic efficiency. So for any intake, this isentropic efficiency or adiabatic efficiency should be close to that of 1 or 100%. That is, the ratio should be close to that of 1 or 100%, but you won't get 100%, but we should try to get closer to that of 1. So the next performance parameter for your both subsonic and supersonic intake is that the pressure recovery factor or the stagnation pressure ratio. Okay, so what is this pressure recovery factor or what is the stagnation pressure ratio? Since you see, to take the Bernoulli's equation, P naught is equal to P plus of rho V square. In a process, if there is going to be a reduction in the static pressure, that doesn't mean that that is a reduction is due to loss. That may be due to acceleration of your flow. Okay, so but if there is going to be a reduction in the P naught, that refers to loss in your process. Okay, so what is this? Another parameter which we use to measure the performance of your intake is that stagnation pressure ratio or pressure recovery factor. P02, what is the total pressure at the exit of your intake, divided by what is the total pressure of your free stream flow. Okay, so this ratio, what we call it as the stagnation pressure ratio. So since there is going to be a frictional loss when the flow is passing through a subsonic intake or when the flow is passing through the supersonic intake, due to this formation, there is going to be a loss in the total pressure. So this RD is going to be always less than 1. But so we have to design in such a way that your value RD, pressure recovery factor, should be close to that of 1. That means the loss, total pressure loss happening in that particular conversion process is of less or negligible amount if it is close to 1. Okay, so these are all the two parameters we use to measure the performance of our subsonic as well as supersonic intake. Okay, so with this, I'll complete this today's class. So what we have discussed in the today's class, we have seen about under different inlet Mach number, what is happening inside your supersonic intake. Okay, when your flow becomes supersonic, there is a formation of shock wave. How do we move the shock wave to the required location, that is slightly downstream of your throat location? So you know why we have to situate your shock slightly downstream of your throat location, because in that location only your Mach number is slightly greater than 1. So the shock wave forming will be having the weakest strength. So when the flow is crossing that, you will have the least amount of total pressure loss. So this process of establishing the stable shock downstream of your throat location. Okay, that's what we call it as the starting of your supersonic intake. So after that, we have discussed about the parameters we use to measure the performance of our intake. Either it may be a subsonic intake or supersonic intake. They are stagnation pressure ratio. Another one is the isentropic efficiency or adiabatic efficiency.
Like, share and subscribe. Hit the bell icon for more updates.